Okay, welcome all to another live session of TIFR Math problem solving. So this problem heavily relies on two concepts. That is, uh, what are the eigenvalues of real symmetric matrix, and that every symmetric matrix is always diagonalizable. So these are the two things that you practically need to solve this problem, or to say quote unquote to prove it or disprove it. Okay. So since A in R is symmetric, this implies A is diagonalizable. So in turn, what happens is that this implies trace of A to the power n is equals to summation over lambda I equals to 1 to, let's say, m to the power Ri. So where I'm actually, since it is diagonal, I'm taking that lambda 1, lambda 2 up until lambda m. These are the distinct eigenvalues that are occurring some R1 times, some R2 times, and similarly some Rm times. Okay, so that is how the trace of trace of A to the power n is lambda I whole to the power n. Okay, so the diagonalizability condition kind of takes care of this. That if you have trace of A to the power n and these are the distinct eigenvalues, then you get trace of A to the power n equals to lambda I whole to the power n. Now what you need to show? You need to show something like this. That is it true or not? The trace of A to the power n, that trace of A to the power n is less than equals to this and greater than or equals to this. So now, if you look at this from this angle, that if you take modulus of trace of A to the power n, so this is precisely mod of summation over I equals to 1 m lambda I to the power n. Okay. So now they are saying that given you will always find such a matrix. What they're saying is that you will always have such a matrix of order R cross R such that this term is always bounded. That is why uh, this things comes, that symmetric matrix says that for all n belongs to n, we have this. For all n, you will have this. That means what? Trace modulus of trace is always bounded. Okay, but think about it from this perspective. So modulus of summation over lambda I whole to the power n, I equals to 1 to m. So this is always less than or equals to summation over modulus of lambda I whole to the power n, I equals to 1 to m. So this is the basic triangle inequality. So by usage of the basic triangle inequality, you can establish this fact. Okay. So now say mod of lambda i's are less than 1. So if mod of lambda i's are less than 1, this actually implies that this series that you are taking . by 2 to the power root n, this will tend to 0. Okay, the reason is this being less than 1. So if you take this summation over mod of lambda I whole to the power n by 2 to the power root over of n, the 2 to the power root over of n will dominate it if you take limit n tends to infinity. Okay, so this will always tend to 0. Okay, so now from here you have one way contradiction. So what is that contradiction? That if it is tending to 0, then for all n, trace cannot be greater than equals to 1, because what we are actually proving that mod of trace is less than equals to modulus of this, and this will go to 0, hence this will go to 0 since it's a mod. I mean by modulus of 2 to the power root n divided by 2 to the power root n, this will go to 0, and thus the left hand side doesn't hold if I have mod of lambda i's less than 1. So now what happens is that whenever we take, let's take for some I lambda I, mod of lambda is greater than 1. So if mod of lambda I becomes greater than 1, then for large enough of n, if we just separate that lambda I, so summation over lambda I whole to the power n, I equals to 1 to m. Now you're writing, let's say for some I equals to j, mod of lambda j is greater than 1. So you're writing it like this, lambda j to the power n plus summation over I equals to 1 to m lambda I to the power n. So where I is not equals to j. So this sum can be broken into this part, right? But now since this is greater than 1, so if it was bounded above by this part, if it was bounded above by this part, then by n tending to infinity, this should have been bounded, right? Only then the modulus will be bounded. So if you take n tends to infinity, since this lambda j is greater than 1, this part shoots towards infinity. Hence, this cannot be bounded. Thus, there cannot exist an upper bound in this problem. So, what we have proved that no upper or lower bound can exist. Hence, this statement is inherently false, because these are the only two ways that, see, once we are taking all of them are less than 1, then we are taking at least one is greater than 1. So if all of them are greater than 1, then of course it is not bounded. The sum will never be bounded for arbitrary large n, right? But since even if it's true for only one, so what happens is that you get an unboundedness from above in this part, and unboundedness below from this part. Okay, so there is no surety that there exists such a thing. Hence, answer is false. So thank you. Yes, Rakesh. Alright. So thank you for joining. We will meet with another problem from TIFR in our upcoming sessions. Yes, Rakesh, if you are there. Fine. So we will meet in our upcoming sessions. Thank you for joining.